Let's talk about conformal transformations. So what are they? To start with, let's again look at our friend, the analytical function. So we have an analytical function, f of z, which basically takes as an input a complex number z, and it spits out another complex number, f of z, which we're going to call w. So in essence, this analytical function is a transformation from a certain input z to a certain output w. And we can also look at this from a geometrical perspective as a transformation from a certain z-plane to a certain w-plane. So in the z-plane, we have the x-axis and the y-axis, and in the w-plane, we typically call the real part of w u, and then here we have v. So let's consider, for example, a certain point in our z-plane, that point z0. If we feed that point z0 to our analytical function f, that will get transformed into, for example, this particular point here, w0. We can play this game for any point that we like. So we can also play this game, for example, for all points in the z-plane along a certain curve here. So if we play that game, we can transform that curve from the z-plane to the w-plane, and that gives, for example, another curve here in the w-plane. Now, if you look at that point z0 and a neighboring point here, z0 plus delta z, then that neighboring point will also get mapped to a neighboring point on that same curve here, w0 plus delta w. Okay. Now, what we're going to do is we're going to take the limits of this delta z thing going towards 0. So we're going to let these 2 points approach each other while still, of course, being on that particular curve. You know what's going to happen from basic calculus. The line segment that joins these 2 points will eventually end up as a tangent here to that curve in the point z0. And the same thing will happen in the w-plane. So the line that joins these 2 points will eventually, in the limits of delta z going towards 0, end up as, and let's draw this also as a dashed line, will end up as the tangent to that curve in the w-plane. Okay, and then for no good reason, I'm interested in the angle that these tangents make with the horizontal. So let's call, for example, the angle that the tangent makes in the z-plane theta. And let's call this angle here with the horizontal, let's call this angle phi. And I'm interested in theta and phi, and more specifically, the relationship between them. So how does our function f of z changes an angle theta here into an angle phi? And see if you can figure out what's going on here. So pause the video and think about the definition of derivative, because we're dealing with analytical functions. Derivative should exist, and see if you can link the derivative as a definition of stuff going towards 0 to some of the quantities that we've been drawing in this diagram. So pause the video and see if you can figure out a relationship between theta and phi. Right, so our derivative is, of course, the f dz. It's another way of writing f prime, and yet another way of writing that is dw over dz. And by definition, that's the limit of delta z going towards 0 of the corresponding delta w over the delta z that we're looking at. This is just the definition of derivative, and we see here these quantities delta w and delta z going towards 0, which is exactly what we've been doing in these diagrams. So now we're interested in angles. So this basically suggests that if we have this expression over here, we just look at the arguments of those expressions. So here we have the argument of the derivative, df dz. And then that's also equal to the arguments of that limit thing here, which I'm going to copy. So the limit delta z going towards 0, delta w over delta z. Now we know if we have an analytical function that the FDZ exists and is independent of direction of approach. So regardless the angle here, the derivative is the same. So this has a certain angle, a certain value, which we're going to call by definition alpha here. So alpha independent of direction of approach is the argument of the FDZ in our point Z0. And then for the right hand side, well, you know, if we have the argument of a quotient of two complex numbers, that's basically the difference of the arguments of the numerator and the denominator. Very easy to see if you write this in a polar form. Let's play a bit fast and loose with the order of the limit here. And then we can say that this is then equal to the argument of the limit of delta z going towards 0 of delta w minus the argument of, again, the same limit delta z to 0 of delta z. And now it's just a matter of identifying what's going on here. So if we look, for example, at delta w in the limit of delta z going towards 0, well, this is what we were talking about earlier. This is the line between two neighboring points here that will eventually end up as the tangent. So this is this particular line here. And then if you then take the argument, that's basically this angle over here. So this is going to be our angle phi here. And then very similar, this actually, if you look at the diagram, is the angle of the tangent in the z-plane. So this is going to give us theta. So here we have our relationship. We have that the angle of the derivative sets a relationship between these two angles. Or after some very complicated and grueling algebra, we can conclude that the angle in the w-plane is actually equal to the angle in the z-plane plus the alpha, the argument of the derivative at that particular point. So here we have a cool relationship between these two angles. And again, this is true for every possible direction of approach. So for every possible angle that this curve makes in the z-plane. So this is true not just for these particular curves that we've studied. This is true for any particular pair of curves that you can draw. So if you have, for example, one pair of curves, we can write down that phi1 is equal to theta 1 plus alpha. But if you have a different set of curves related by the analytical transformation, then you can also write down the following. And that means that if you subtract these, that the difference in angle in the w-plane is equal to the difference in angle in the z-plane. And that's very fundamental, because that means that if you have in the z-plane, let's say, two curves which make a certain angle with each other, okay, so this is roughly an angle of 30 degrees, let's say, then you know by the argument that we've been building here that if you look at the angle between these two curves in the w-plane, that you should have exactly the same angle. So let's say, for example, then these curves are like this. So as a whole, they could be rotated. But the important part is that the angle between the curves is kept constant after the transformation. So there's a very fancy name for a transformation that keeps the angles between two curves intact. And that name is, you guessed it, the conformal transformation. So a conformal transformation keeps the angle between two curves constant, and you can build such a conformal transformation by having a look at an analytical function which has a certain non-zero derivative and building the arguments that we have here basically. So this is an introduction to conformal transformations.